Namaste everyone. Welcome to first lecture of application of derivatives. This is Rajesh. In this lecture, we are going to see syllabus and our first application, that is rate of change of quantity. So let us start with syllabus. Rate of change of bodies or rate of change of quantities, increasing and decreasing functions, tangents and normal, use of derivatives in approximation, maxima and minima, first derivative test motivated geometrically and second derivative test given as a provable tool, and simple problems that illustrate basic principles and understanding of the subject as well as the real life situations. Now let us see rate of change of quantities. Let y is equals to fx be a function of x, then dy upon dx represent the rate of change of y with respect to x. Also, dy upon dx at x equal to x0 represent the rate of change of y with respect to x at x equal to x0. So what you understand by this statement? That if y equal to fx is a function, then dy upon dx represent the rate of change of y with respect to x. That means change in y when there is a change in x by unity. That is rate of change of y with respect to x. So per unit change in x, what is the change in y? That is your rate of change, right? And this rate of change, if it is different at different time or different values of x, then for different values, like when x is equals to x0, we find dy upon dx at x is equals to x0. So in dy upon dx, we put x0 in place of x, and that gives me rate of change of y with respect to x when x is equals to x0. Now if x is f of t and y is g of t, that means x and y, they are two different functions of t, then in that case by chain rule we can find dy upon dx. That means in that case also we can find rate of change of y with respect to x, and that will be given as dy upon dt whole divided by dx upon dt. Now let us understand this with the help of one example. The volume of cube is increasing at a rate of 8 cm cube per second. How fast is the surface area is increasing when the length of its edge is 12 cm. Okay, so there is a cube, okay, which is changing its dimension and therefore its volume is increasing. Okay, so as volume is increasing, definitely edge length will increase and definitely surface area will also increase. We have to find the rate of increase in surface area, right, when edge is 12 cm. So let us see how we do this. Let length of edge of cube is x centimeter, as cube is there but its length we don't know, so randomly at one point we consider let the length of edge of cube is x centimeter. We consider v with the volume and s with the surface area. Then for cube we know that v equal to x cube and s equal to 6x square. Now what is given? We have given dv upon dt. Okay, you can see here it is 8 cm cube per second. So per unit time there is a change in volume by 8 cm cube. So dv upon dt is given 8, and what we have to find? We have to find ds upon dt. Now this dv upon dt equal to 8, it gives me d upon dt of x cube, as volume is x cube. So d upon dt of x cube is 8. Now we differentiate this x cube with respect to t. What we will get? We will get 3x square into dx upon dt. Here x is a function of time. As time is changing, the value of x, that is edge length, is also changing. So this is a composite function, right? So its derivative is 3x square into dx upon dt, which is equals to 8, and from this we get dx upon dt value as 8 upon 3x square. Now let us find ds upon dt. So s is 6x square. This gives me ds upon dt as 6 into d upon dt of x square. Again as x square is a composite function of time. So we say that ds upon dt is equals to 6 into 2x, derivative of x square is 2x, into dx upon dt. Now the value of dx upon dt we have already find here, which is 8 upon 3x square. So we replace this dx upon dt by 8 upon 3x square and simplify. The simplification gives me ds upon dt as 32 upon x. That means rate of change of surface area, it depends on the value of x. Now we have to find the rate of change of surface area when edge length is 12 centimeter. So we replace this x with 12 and we get ds upon dt is equals to 32 upon 12. On simplification we get 8 upon 3. Now unit we have to mention if it is given. So as unit for volume is centimeter cube, unit for surface area will be centimeter square, and we say that ds upon dt at x equal to 12 is equals to 8 upon 3 centimeter square per second. I hope you understand how to calculate rate of change. Okay, rate of change using derivatives. It is very simple, right? Okay. Now let us see marginal cost and marginal revenue. Now this is something related with commerce stream, right? But here also rate of change is involved. So let us study what is marginal cost, what is marginal revenue, and how it is related with derivatives. Marginal cost represent the instantaneous rate of change of total cost at any level of output. Now instantaneous rate of change, that means again it is change in cost upon per unit output. What they have said, marginal cost represent the instantaneous rate of change of total cost at any level of output. Output means the number of units which we are going to produce. So if Cx represent the cost function for x unit produced, then marginal cost MC is given by MC equal to d upon dx of Cx. So Cx is some cost function and which x is the number of units produced, then marginal cost will be derivative of this total cost. So MC is d upon dx of Cx. So that's it. You will find by using this formula what is marginal cost. Now in the same way, let us see what is marginal revenue. So marginal revenue represent the rate of change of total revenue with respect to number of items sold at an instant. Okay, so if Rx represent the revenue function for x unit sold, then marginal revenue is given by d upon dx of Rx. So in this lecture we will stop here. In this lecture we have seen rate of change of quantity. In our further lecture we will see few more applications. Now here we have seen only concept. In our further videos we are going to see problems based on this concept. Thank you.